in the connection. And so you'll see in the tables that for slip-critical connections, the bolt strengths are given according to the different hole types. Usually what they do is on these problems, they give you standard holes, and you don't have to worry about a lot of this. The bearing type bolt strength, where we're assuming that we get slippage in the connection, is given by this equation. It's all defined here below. But again, we pick all the values out for the various bolt diameters by a table. And don't waste your time using this equation. Slip critical, it has other tables. What's new in the second edition is the fact that you can now base the design on factory loads. With slip critical bolts, in the past you'd base the design on service loads because that's where you didn't want the slippage. Again, you didn't really care if the joint slipped at the maximum all-time load. This is the equation to calculate the strength for a single bolt, but again, it's given in a table. On the next page, what I've given you is a table that kind of summarizes a series of tables that are in the specifications. For the second edition of the LRT specs, it's in volume 2. It's in that second volume. But again, note that the values, for all the values, they have single shear and double shear. And note that the values are just double for the double shear, which would make sense. And here I've given you it for various bolt diameters. Again, note for the slip critical bolts that they give values for the different type of holes that you can have. When you get into the bearing type, the N and X's, then it's just the standard or the short slotted that is perpendicular to the line of action.
So they won't let you use the other kinds?
Yeah, you can't have going back. You can't have a bolt and bearing that with a load that's parallel with the longitudinal axis of the oversized hole, because it's just going to slip right down, or actually the hole slips down right off the bat. Okay, you can only have this or this in bearing, but the oversized can only be a max of a 1/16 of an inch. Whereas in slip critical, because it's getting clamped together, you can have the various orientations of the hole. You have to watch out for bolt spacing. You don't want so that should be the minimum bolt spacing. You don't want the bolts too close together, otherwise they kind of interfere with one another. Can't be any greater than or any closer than 3 times the diameter of the bolt, but typically you use a standard dimension of 3 inches. Edge distance, to keep it from pulling out the edge of the member, 1.5 times the diameter, or 1.5 inches for 1 inch or less diameter bolts. Now this type of failure, we call it a tear-out failure. Now anybody, I think I see in the front a 3-ring binder notebook. Okay, that failure is similar to taking a page and yanking on it and it tears out. Okay, you know, there on notebook pages, we got these little reinforcer tabs that we can put on those little donuts that will correct the problem. Here we don't have that. You got to make sure you got adequate spacing. Another thing you have to worry about with bearing bolts is the bearing of the bolt against the plate. It'll cause a high compressive force to develop here, and you'll get yielding, and the bolt will begin to plow through the plate. The strength to prevent that is defined by this equation here, and where D is the diameter of the bolt, actual diameter. You don't have to add like a 1/16 or an 1/8. T is the thickness of the plate that you're checking. Fu is the ultimate or tensile strength of the plate material. Looking at an example, let's say we have this simple lap splice where we're lapping two 1/2" by 6" plates together. We're going to use 4 bolts. Okay, because there's only one plane in the connection, the bolts are going to be in single shear. We're going to use A325N bolts with standard holes. They're 7/8 inch diameter. We're using A36 steel. Okay, from the table, you can also pick this off the table that I gave you, but the strength of a single bolt is 21.6 kips. You have 4 of them, so the total strength of the connection based on the bolts is 84.6 kips. Gross section yielding of the plate, again, it's a tension member. Running through those numbers, which we've seen before, it's 97 kips. Net section fracture, again, what can happen is it can fracture through these 2 bolt holes. Again, like we saw in the tension member section, running through that calculation, it's 87 kips. Looking at bolt bearing for a single bolt, running through the formula we saw 2 pages previously, it's about 47 kips, but it's per bolt, so we have 4 bolts, so it's 183. Just quick check on the spacing, everything's adequate there. And so what happens is the lowest value we get from everything we checked is 87 kips, and that was net section fracture of the plate. So that is what controls the design. When we get into connection design, you'll see that this is similar to block shear that we looked at, but we can also have a net section fracture of a member or connection. And now, because it's shear, the forces are going like this. What happens is that the failure occurs through the bolt holes, but parallel with the shear force. And that's calculated similar to net section fracture, where we take the gross area and deduct out the area of the holes. Typically, you don't have any staggers, so you don't have to worry about that. But, again, then the strength is given by the net area times FU, because it's a fracture, 0.6 because it's shear, and a reduction of 0.75. Sometimes what happens is that we'll load bolts such that we'll have a bolt pattern or grouping where the force doesn't go through the centroid of the bolt group, and when that happens, not only are the bolts subject to shear, but they're also subject to a torque due to the eccentricity. Okay, when that occurs, you can use 2 methods. One is called the vector elastic method. It turns out to be conservative, but it's not really correct, and it's given by this. You go into some of the example problems that we sent up in those books and look at it. I think you went over something like this previously with Dr. Lowery. They do give you tables, though, that allow you to calculate the strength directly, and I referenced that for both the second and first edition. But it's based on a different method of calculation. I'm not going to show you that, but it's called instantaneous center of rotation method, and it's actually what happens in the connection. The tables look like this. A little hard to figure out to begin with, but it's easier to look at an example on the next page. Say we have this connection. It'll be typical of some bracket that supports some type of crane rail. Say we've got A325X 7/8 diameter bolts. It's going to be in single shear. We've got 6 bolts arranged like so. Should be equal spacing, although I don't think it is the way it printed out. We want to know what the design capacity is. Okay, from the table, given that the shear strength of a single bolt is 27.1 kips. But now we go to that table, and there's a series of tables, but we go and pick out the one that looks closest to our connection. And we need to go in with, by the problem definition, it was an eccentricity of 10 inches. The spacing between our bolts was 3 inches. Actually, I picked off the wrong one here, so it's not going to work for here, but we had 3 inches here. What you do is you find your eccentricity, it's 10, the spacing is 3, you also have 6, another group of numbers for a spacing of 6 inches, and then the number of bolts in one vertical row. For our problem we had 3, so you have 3, you come in and pick off a value. Okay, for this table, which is wrong because the spacing between the bolt lines is 5.5, it should have been 3. Maybe did I give you the correct one? Yeah, okay, so you have it. Here it's 1.8, but I think on the correct table you come up with a C coefficient that's 1.46. You take that value and multiply it by the strength of a single bolt, so it's about 1.5 times 27.1 gets you almost about 40 kips to round off. But what the C does is take into account the reduced strength of the bolts because of the eccentric loading. And a way of getting a feel for that is if this force went through the centroid, what would be the resisting force of the bolt group? Anybody know or venture a guess? Well, how would we calculate it? It'd be the strength of a single bolt times the number of bolts.
Because you don't have any moment.
Okay, there's no moment, so all the bolts get subject to shear, pure shear. Okay, so it'd actually be 6 bolts times the 27.1, or the strength of a single bolt. That comes out to be about, 175 or something?
About 180. Yeah, 175, something like that.
175. What the C value does, take into account the reduction in strength due to the eccentricity. So it's like, the C is kind of like the equivalent bolts that you have left over to resist the shear force. That's actually 163 kips. Okay, so it's like the moment, the torque that's caused by the eccentricity uses up, a
bunch.
4.5 bolts, and you only got 1.5 bolts left over to resist the shear force. But again, it's all taken into account by the tables. Looking at welds, quickly, the weld types, you have fillet welds, partial and full, for complete penetration groove welds, plug and slot welds. Typically what you see on these problems are fillet welds. That's what we'll concentrate on. Welding processes that you have, and you need to know this because you can actually adjust the strength of the fillet weld based on the process, but it's shielded metal arc welding, and that's the process that you usually see. It's the stick rod that you'll see being done, and then there's another process that is typically done in a fabricating shop. I believe the book that textbook we sent up there is wrong. They got these reversed for some reason.
In that brown book?
Yeah, in that brown book.
Well, we'll have to take a look and verify that.
What happens when you weld is you actually deposit weld onto the plates that you're connecting. That's called filler metal. You need to know the strength of that. Typically what you try to do is match the strength of the weld metal with the base metal. It's called matching weld metal. If the base metal has a yield of 36 or a FU of about 60 KSI, then you want to use what's called the E60 electrode. If the base is 50 KSI or 70. At ultimate, then you use E70. And note that you're matching the tensile strength of the base metal. In reality, typically what they do is probably use E70 for both the 36 and 50 grade steel, just because it allows them to use the same electrode for both plates, and these are the more common strengths or grades of plates that are used in construction. The fillet weld strength is derived by calculating the effective area of a weld times the maximum stress that can develop across that effective area. And the effective area is given by what's called the effective throat, which is the minimum distance from the root of the weld to the face of the weld. So it's this diagonal distance here. But typically when we size a weld, we use or specify the leg dimension, which is this, because that's what we can actually measure or see. So now the throat, or the effective throat of the weld, is actually 0.707 times A, which is actually what? It's 1 over the square root of 2 times A.
Cosine 45.
Or cosine 45, or sine 45. Times the maximum stress. Okay, what we're going to do is calculate the unit strength, or the strength of the weld per inch of weld. So the stress that can develop is the strength of the electrode times 0.6, because it's a shear failure again, times the phi, which is 0.75. And again, this gives us strength in kips per inch of weld, and you can calculate this value for a 1/16 of an inch weld size, because typically what they do is they designate weld sizes in 16-inch increments. A real common weld size is 5/16 of an inch, because that's the most weld size. That's the largest weld size you can put down in one pass. Okay. The problem with welding is you got to clean off each subsequent pass, and that takes time and then money. Fillet welds are used in lap splices and in corner and T-joints, as you see here. Again, you design with a common size of 5/16. Watch out, if you lap here, the weld size can't be any greater than the thickness of the plate minus a 1/16 of an inch, and that just keeps you or the welder from burning off the edge, but it is a limitation on the weld size that you need to be aware of. Okay, I gotta crank things up so we can get out of here in 1 minute.
I want to see that.
But here, this example was an error in your notes. I've corrected it. The corrections are, I had to change it to make it work after I made some of the corrections. But I changed the plate to, I think I had an 1x8. I made it 1x6, and a 1/2 inch by 6. It's now 3/4 by 4. But you wanted to design the fillet weld for this plate here to carry the load, maximum load that could occur in this plate. That would be based on gross section yielding, so it's about 97 kips. If we use E60 electrode, then what we do is we take that design load, phi p sub n, divided by the strength, the unit strength of the weld, and that will give us the required length. It comes out to be about 10 inches, so we'll put 4 inches here and 3 and 3 on a side, and that balances the design. So it's pretty simple, relatively simple. Watch out, you can have eccentric loading of weld groups like you do bolts. Again, so you get it all? Yeah. Yeah, that problem got all messed up when I converted these notes from allowable stress design to LRFD. it kind of got changed halfway.
So what did you change now? You changed the 6?
I think this was 1/8.
So it's now 1/6.
1/6. This was 1/2 by 6.
So it's now 3/4 by 4.
And 3/4 by 4.
Okay.
And this was wrong. This was like 0.6 or something.
Yeah, because that's allowed stress. So now we're going to the LRSD.
It was 0.6. Should be 0.9. I've changed the area that smaller plate, so it's
Sure.
0.75 versus 0.5,
Yeah, well,
and it's 4 versus 6.
Yeah, that's these two numbers.
Yeah, this is all right there now.
Right.
And then that gives you a different value. It's 97, and then I think everything else. No, this was wrong. That it should be 0.75. It was 0.3 before, because that's allowable stress.
Right. Okay, so it goes to 0.75.
And that came out to be 16.3, but it's actually 9.8. So.
Quite a difference in allowed stress design, huh?
Okay. Well, it wasn't. It was I was mixing the two, so it was actually junk.
Okay.
Again, the welds can be loaded eccentrically, much like the bolts. There are tables there. I'm not going to go into it in detail. There's the table, similar, although a little more confusing than the bolts.
Well, let's see. He's got pretty much the same thing. Okay.
I do give you an example. If you have time, you might go through and look at that. But again, the design's all tabular. It's just a matter of making sure that you enter the table with the correct numbers. Complete penetration groove welds. In a sense, what you're doing is just putting back in the metal that you had to get a full cross section. Consequently, all you got to do is match the weld metal. There's no design involved with complete or full penetration groove welds. In partial penetration groove welds, what happens is the strength of the weld may not be equal to the strength of the plate, so you actually have to calculate the strength of the weld. That's given by the strength of the weld metal times its area, and the strength is 0.6 times the electrode strength, E60 or E70. Again, you still assume a shear failure, a phi of 0.8 times the area of the weld, which is the effective depth times the width, and the depth may have to be reduced if the groove angle is narrow, just because you can't get weld metal down to the base of the groove. What can happen, though, is depending upon the strength of the weld metal, if the strength of the weld metal is real strong, what will happen is you'll end up tearing out the base metal before you reach the strength of the weld. So you got to check the base metal strength also, and that's given by this equation here. Connections, steel connections. We have two types: simple connections where we carry only shear, and moment connections where we carry the shear and moment. Going real quickly again, in a shear connection, a common one would be the double angle connection, where we use two angles and bolt the angles into the web of the beam and into the column, probably the flanges. The way to do connection design is to try to follow the force through the connection step by step, and I've outlined that for you by numbering this exploded view, and in the next page it shows the steps. They've got tables for everything. They've got the bolted double angle connection tables. They're in the second volume of the second edition, and again it's fairly self-explanatory. As an option to bolting, you can use a fillet weld, usually more economical. Another type of simple connection would be a beam seat. You provide a little ledge or seat, and so exploding it, you can see the steps that you have to go through. They're outlined here accordingly. In the next page, looking at the connection in side view, what it comes down to actually is sizing the angle, which turns out to be like a cantilever beam, but sizing it so it's thick enough such that you don't exceed the bending capacity right here at the critical section, and the critical section is taken as 3/8 off the inside face of that angle. And there's a design procedure that's given in Volume 2. Volume 2 has real good example problems if you get a hold of it. In moment connections, what we're doing is, again, we're trying to develop moment capacity in the connection. Typically, we're taking the moment that's occurring in the beam and resolving it into a force couple system by taking that moment divided by the moment arm, which we call dm, and coming up with a force which we assume to act at or near the flanges. And so typically the design of the moment connection revolves around resisting these forces here. We still usually have shear in the beam, so we use one of the other connections to carry the shear. A simple connection. Typical moment connection would be as shown on the next page, where we'll come in, we can use full pen groove welds to weld the flange into the flange of the column and then carry the shear through a bolted connection here. Okay, it's a real typical standard detail. We used to think it had good resistance in earthquakes, but the earthquake we got in Northridge last year, a lot of these failed. And it was a big shock to the steel industry. Not a problem here, but not good in California anymore. Another way of delivering the force that develops due to the moment to the column is to use flange plates that sit on top or below the flanges of the beam, and we either weld or bolt those in and deliver the force out here. The problem with moment connections is that even when we've adequately handled this force or transferred it from the beam to the column, we still have to worry about it as it goes into the column. What can happen is it can either, the tensile force can bend the flanges of the column or end up yielding the web of the column right there, or it can buckle the web of the column or crimple the web of the column right here. So typically what you have to do is add stiffeners here and here to prevent that or resist that, and there are procedures for that given in Volume 2. Now they're plates, they're just stock plates. Simple. Okay, that completes it for steel. I know I've run over, but any questions on steel?
Well, let's see, I missed a little point on page 62.
If you plan on doing the steel problems, I'd recommend getting, you need the manual, because you need the section properties, but the manual has real good example problems in there. And just get to know where everything is. Because that, if you get lost, you're going to spend a lot of time flipping through that manual. I do have a section on timber design. I'm not going to go over that other than to tell you that if you think you want to do timber design, or anybody out there ever do timber design? Sort of.
one guy's a timber man.
What you're going to have to do is get these manuals. One is the specification, the other one is the supplement. You can't do timber design without these because you need the design values that are in here. You don't have a prayer otherwise of doing it. They can be obtained from the address that I give you here for some nominal cost. Not as expensive as the steel manuals.
Well, and the notes you got there are pretty good too.
Yeah, go through the notes and you'll see that problem with timber is that the strength varies depending upon the direction of stress and the species and types.
Yeah. First off, you can always reach Pete. Whoops, let me see here. You can always reach Pete through the email, and then phone number.
(409-845-9969). That's actually a pizza joint for us, though.
But how about your email?
You want email?
They might be able to hit you there now since we're on their computer. Okay, and if that one doesn't work, write me down there. Lowery and I'm at the same thing, just tamu.edu. That one I know works. I'm not sure if Pete's is connected into your system yet, but mine is definitely connected into the system.
Yeah, if this one works, that should work.
That's probably true. Should be able to hit Pete with email, and it's free.
Yeah, it'll be, I'd be glad to answer questions. Good luck to you. Okay.
Okay, we'll see you guys next week then. I guess the next one is Wednesday. Is that the next one? All right. Wednesday and Thursday, that'll be Cal Woods.
You want these?
Yeah. Tell you what, I like that whole setup.
I'll print you out.
Okay, that'd be